So hello everyone. So today I will talk about like a brief story of the quantum Hall effect in graphene system. So this work is actually ongoing work with Professor Sumati Rao and Ganpati Murthy from University of Kentucky. Okay, so before going to the quantum Hall effect of the graphene, let me first give a brief introduction of what the graphene is. Actually, maybe all of you are familiar of this thing, but let me go through it 1 second. So actually, graphene is like a 2D sheet of a graphite, and you exfoliate from a graphite. So what you will find that it has like a two inequivalent sides A and B in a periodic manner. Now, if you try to write a simple theory which can explain the electronic properties of this system, you will write a simple tight binding Hamiltonian like this, only considering the outermost orbital of the electrons. Now, you solve this problem by going to the Fourier space and diagonalize this Hamiltonian. You will get some spectrum, but then you will find that there are 2 points in the spectrum where the the spectrum is gapless. These are 2 points in the Brillouin zone, and which we call, let's say, K and K prime. And if we only just think about low energy physics around these 2 points, actually we will see that the spectrum looks linear like this. So if you just take some momentum around this point, you will find that this is the P. So you will see that the spectrum has a P dot sigma term. The sigma is the Pauli matrices in this K and K prime valley. So for this talk, we will only interested of this this kind of spectrum close to this K and K prime point. Okay. So okay, so let's say we know the spectrum of the graphene. Now before going to then we want to put some perpendicular magnetic field to the system along that perpendicular to the plane of the system. So now before going to the Landau law in the graphene, let me just briefly tell you what we will get the spectrum in when the dispersion is p square over twice m. So low energy dispersion is of the electron of p square over twice m. If you put the same orbital magnetic field, we will using the piles substitution, we will see that the Hamiltonian behaves like this. Now, if you quantize this Hamiltonian, you will get some harmonic oscillator levels, and this is the characteristic energy we will find in presence of magnetic field. This is the cyclotron energy, and you do the similar algebra here and just take the linear dispersion and do the similar pile substitution here. You will see that the spectrum instead of this linear to the n, you will see that the spectrum has like square root of n behavior. And interestingly, the magnetic field appears here in this spectrum with respect to this magnetic length. So this magnetic length, so the picture the spectrum as behaves as a square root of n only validates in the truly speaking when this magnetic length is larger than very large than the lattice spacing, and typically the laboratory magnetic fields are in this limit. Okay. So with this, so let's say what is the main difference to keep in mind from the basic 2D electron gas and the this graphene quantum Hall this Landau level spectrum. So in the 2D electron gas, you will see that the spectrum is linear with respect to n, and if you take a perpendicular cut like this, vertical cut, you will see that the successive gaps are same. But for the graphene case, it's like a square root n, and also the thing is that the gaps actually keep on decreases if you go farther and farther higher in Landau levels. And these behaviors with respect to a perpendicular magnetic field actually helps you to detect whether the behavior of your material is like a relativistic quantum Hall effect or like a 2D the integer quantum Hall effect. And the interesting fact is that is also different from this the 2D electron system is like that you will have the similar structure. So previously I was showing you this for a particular value. You can do the similar thing for the other value also, K prime value, and you will also get the similar structure. So you will have like two valley degeneracy and also the spin degeneracy in the system. So that is why you will get the fraction, the filling fraction in the like multiple of 4 of n, and this is different than the 2d electron gas, where you will only get has the spin degeneracy, which has like the filling will have the 2 times n. So these are like the main differences. Okay. Now for the like all of my talk, I will only focus on this n is equal to 0 manifold, and I will forget about all other Landau level for this space. So if you think about this 0 Landau level manifold, what you will find that if you solve this problem, particularly for the 0 Landau manifold, you will see that the sublattice like A and B sublattice in a particular sublattice, you will see that this will only, the wave function will only have the support from either k or the k prime value. So your problem like simplifies, you will have only have the problem will have reduced with a 4x4 Hamiltonian structure. Now and in this k up, k down, k prime and k prime down basis, you can solve the Hamiltonian. Now what people found, like, so let's say in all real system you will have some finite Zeeman energy. So what this will do, this will create a gap in the bulk, because that will, the finite Zeeman energy will polarize the state to a like upspin. So there will be a finite gap between the upspin sector to the downspin sector. And early 2006 people so if you take this structure and you put a edge, what you will find that this due to this k and k prime structure, one will like close to this edge, one will go upwards and one will go bend like let's say the k will go upwards and the k prime will get bent downwards. So and the similar structure will have there. So if you take a like chemical potential, put your chemical potential like this, what you will find that that chemical potential will cut in 2 points. One, so you will have like a like forward propagating mode with a upspin and one a backward propagating mode with a downspin. So you will have at each edge like 2 counter propagating edge modes with opposite spins. That this opposite spin is important. That actually help you to help you to protect this edge with respect to some disorder, and also the Coulomb. People have done will also using Coulomb interaction in this edge, and people found that this doesn't change the nature of this edge states. It's only get a Latinger liquid behavior. Okay, so all of this good. Now after this it took a lot time to actually do the experiment on this graphene system. So this is like a famous experiment on this system where this is by the Andre Young group. So what they did, actually they took a 2D sample of graphene and they tuned the gate potential close to this point where the filling fraction is 0. Now what they have put in is like they have with the perpendicular magnetic field, you can put an in-plane magnetic field. So this in-plane magnetic field only has this Zeeman effect. So it will just tune the Zeeman field. So and what they found is if you increase the Zeeman field, this conductance goes from 0 to 2 square h in the it goes to 2 in the unit of square over h. So okay, so this is their observation. Now comes from the like the theoretical picture. Can we explain this behavior here? So from the theoretical picture, in each edge, what will have like the 2 counter propagating edge, like 2 in here and 2 in here. Now, if you put a source if you want to measure 2 terminal conductance, if you put a source and drain here and put a bias through it, so from these 2 edges, you will see that the red channel will carry current, and from here to this green channel will carry current. So this the non-interacting picture always says that you will have a conductance of 2 square over h. So this is the limit that is explainable from this theory, but clearly this limit is not explainable. So of course, then we need some interaction to explain this system. So then people have found this AC4 symmetric long range Coulomb interaction actually doesn't break this non-interacting picture. So but famously this paper by Kharitonov 2012, what he took is he took some kind of generic this orbital, this k and k prime isospin space. He took some kind of ultra short range interactions in that which doesn't have this AC4 symmetry actually. So using those interaction parameter, let's say the in-plane interaction, anisotropic interaction, and the perpendicular to the plane anisotropic interaction, what he found is like you get a rich phase diagram in the nu is equal to 0 case. So these 2 phases are like they are spin singlet. So for this, the experiment, we only think about these two phases. So this ferromagnet phase is like where the both A and B sublattice has like the spin always points in the along the Zeeman field.
You have 5 more minutes.
Thank you. And the CAF phase is like where you will find that instead of you will see that the spins actually doesn't point to the Zeeman field axis, but it has like some canting angle to that Zeeman field axis. So what happens is the spin actually gains some energy to point in this, let's say, ZX plane. So this is the CAF phase, what you call the cantor antiferromagnet phase. Now the thing is that if you this second order phase line is depend on the Zeeman field. So if you increase Zeeman field, this line shifts to the left. So if you start with a CAF phase, what you will find that after increasing Zeeman field, that you will go to the CAF phase to the ferromagnet phase. Now the question is that does that explain the experiment? So what people did that they took the bulk cantor antiferromagnet, ferromagnet, antiferromagnet states. And if you do with this order parameter in the bulk, and if you introduce the edge, what you will find that for the antiferromagnet, the both bulk and edge are gapped. And the ferromagnet, this is the non-interacting picture, so you will get the 2A square over E conductance. But in the middle, in the CF phase, you will get some kind of crossover. So now if you like tune your chemical potential like this, so depending on the this CF order parameter, you will get the like more and more conductance. So this is where this CF to ferromagnet phase transition in the bulk explain the conductance behavior in the experiment. Okay. So I think I think that is the well described theory. But now our motivation comes from more recent experiments. So here people have found that more than different filling fractions in the apart from nu is equal to 0 in the zeroth Landau level. So actually what this nu is equal to -1 and nu is equal to +1 means is nu is equal to -1 means out of the 4 0 Landau level manifold, you are only filling 1. And this for like you are filling the 3 Landau levels. And these are some STM measurements where people from this Alice Denny group where actually they can detect like in different filling fraction what is the electronic wave function. So we want to actually look at the details of these phases, and also another kind of motivation also comes from another experiment where they have like a different islands of nu is equal to 1, and in between you will have a sweep region where you can change the filling fraction from -2 to +2, and at the end you will get some interface from nu is equal to 1 and -1. So we also looked at this interface from -1 to +1. So okay, so for this to describe these two phases, of course we have to introduce some we took the Hamiltonian but with a parameter G alpha that is different from the Haritono parameter. For his case, it doesn't depend on the Q, but we have to take some finite range in the interaction, because unless you put some finite range of interaction, you will feel that the nu is equal to -1 side, the electron field doesn't feel any interaction. And for this thing, we found that we can either has like a valley coherent states with like both K and K prime valley are occupied, and also like a valley polarized states.
Suman, 1 more minute.
Yeah. So and also we looked at the interface, and also we found that the system transits from a ferromagnet to cantor antiferromagnet in the system. But for this talk, so I would like to go to the conclusion. So what we found is like in the middle nu is equal to 0 region, you can get some more interesting phase transition in the system by introducing this interface, and also the CA phase also breaks this E1 symmetry, so you get some counter propaganda in Goldstone modes, which can explain some Magnon transport experiment in the system. So with this, I want to thank you all.
Thank you, Suman. Yeah, we can have one question. Yeah, thank you, Suman.